Hello everyone, I'm Xuning, a third-year undergraduate student at Xi'an Jiaotong-Liverpool University. It is a real honor to present our paper, Optimizing Moving Target Selection in VR by Integrating Proximity-Based Feedback Types and Modalities. This work was done in collaboration with Wenxuan, Yushi, Zhang, Huang, and Hai-Ning Liang. As virtual reality technology continues to evolve, finding efficient interaction methods becomes more crucial. A big challenge we are focusing on is moving target selection, which is key in applications like gaming and interactive videos. For instance, in Half-Life Alyx, players need to quickly target moving enemies, and in VR football viewing, users need to track a moving player. However, selecting moving targets in VR is a challenging task. Users need to track the target's movement, its trajectory, speed, and depth. We also determine the right moment to press the input device to confirm their selection. This requires a lot of focus and demands a large selection amplitude, making it much harder than selecting stationary targets. That's why many studies have explored ways to improve moving target selection, with techniques like bubble cursor, target ghost, comet, base pointer, and sticky pointer. These methods do improve interaction efficiency, but they also bring along additional drawbacks. For example, they can cause layout confusion, demand extra user actions, disrupt the flow of the sense, and be overly sensitive to parameter settings. To better understand these challenges, previous work have modeled time and endpoint distribution in moving target selection, which also predicts error rates. To address these issues, alternative approaches like feedback mechanisms have been proposed to enhance user experience and task efficiency. One intuitive way to do this is by using different types of sensory feedback, such as visual, auditory, or haptic feedback, either alone or in combination. These feedback types can be applied in different phases of selecting a target. For example, in this video, we are on the Quest 3 main menu. We can see that when the ray hits a target, the controller vibrates and the target turns transparent. When the trigger button is pressed, an audio feedback sound plays. Our work aims to address this gap by exploring the following research questions. First, what are the properties of the partial proximity-based feedback in different modalities? Second, can adding different feedback types across various modalities enhance users' performance in selecting moving targets? Third, what are the properties of binary, continuous, and partial feedback types in different modalities? At last, can the combination of multiple modalities further enhance user performance and experience? Building on previous research on proximity-based feedback, we've defined three types of feedback: binary, continuous, and partial. Partial is a mix of binary and continuous. We've applied three types across three modalities: visual, auditory, and haptic, resulting in a total of 9 variations. We split the target selection process into 3 stages: start, approach, and hit. In the binary feedback type, there's no feedback during the start and approach stages, but feedback is given in the hit stage. In continuous feedback, we start with 30% intensity during the start stage, which increases as the target is approached, reaching maximum intensity in the hit stage. Partial feedback offers a different type of feedback in the hit stage, blending binary feedback. Here's a video demonstrating the visual modality of the 3 feedback types. In Study 1, we aimed to compare user performance and experience across 3 modalities through feedback types and a baseline condition. The experiment was conducted using an Oculus headset in a VR environment. Participants used a controller to select moving targets and press the trigger button to confirm selection when the controller overlapped with the target's ball. We tested 2 target widths, 2 speed, 3 modalities, and 3 feedback types. Our results show that adding feedback has a significant impact on both movement time and error rates. On the UQ scale, the baseline condition scores the lowest in both pragmatic and hedonic quality. Users' ranking and interviews indicated that participants found it difficult to understand depth and movement direction in task results feedback. Therefore, we believe that adding feedback as a cue is key to improving user performance and experience. Interestingly, we also found that continuous feedback performed better than the baseline in moving target selection. This is contrast to previous findings on static target selection. For example, our result noted that for static target, users tend to habitually point at the object since it's stationary and its position remains the same across lots of trails, which lowers the accuracy requirements for targeting. In such cases, users may not fully benefit from continuous feedback. However, in the moving target selection tasks, since the initial movement direction of the target is unpredictable and the target changes the direction upon hitting an invisible, transparent boundary, users cannot rely on initial knowledge or experience to predict the target's position. Therefore, the changes in continuous feedback helped users better understand the spatial relationship between the controller and the target, enabling them to adjust their hand movement. Our objective data also shows the partial feedback outperformed both binary and continuous feedback in terms of selection time and error rates, especially in the visual modality, where partial feedback's advantage is most noticeable. In the auditory and haptic modalities, partial feedback performed similarly to binary feedback, but it's also better than continuous feedback. This pattern is further confirmed by the subjective data, where partial feedback scored lower than binary feedback in terms of both pragmatic and hedonic quality. User feedback highlighted the difficulty of handling multiple layers of feedback. This finding is consistent with previous research, which suggests that layering multiple feedback types in a single channel can lead to confusion and discomfort for users. User interviews also revealed that continuous audio feedback allowed users to quickly perceive frequency changes when approaching an object, but these changes become less noticeable as they get closer, making users less sensitive to the decreasing distance. As a result, binary feedback was considered the best feedback type in the auditory modality. Finally, user feedback indicated that continuous haptic vibration caused discomfort, potentially leading to numbness and decreased sensitivity after prolonged use. Subjective data supports this, showing that both continuous and partial feedback scored lower in user experience compared to binary feedback. In study 2, we compared how different feedback types combined across modalities would impact performance and user experience. The wrong choice of feedback can ruin the design, leading to poor results. So based on study 1's findings, we identified partial feedback type as the best for visual modality and binary feedback type as the best for auditory and haptics modalities. Now, we wanted to see how multimodal feedback compares to unimodal feedback when we use the optimal feedback types. In this study, we found that feedback mechanisms with visual input always performed well in both time and error rates. Feedback results, visual input like audio or audio haptic feedback resulted in higher error rates. When comparing bimodal to unimodal interactions, both visual audio and visual haptic feedbacks performed better. Users found auditory feedback added fun to the task, but visual feedback was key for effective performance. The best overall results came from combining the best feedback from each modality, what we call trimodal feedback. In fact, 62.5% of users rated this setup as the best. Our data suggests that trimodal feedback is the most effective for tasks involving moving targets. This contrasts with a study by Li et al., which found trimodal feedback didn't perform better. We think the reason for the poor results was the use of poor feedback types combination, like color changing visual and varying volume or vibration, rather than the complexity of combining modalities. From our work, we've come up with 4 key design recommendations. First, to ensure repeat and accurate target selection, we recommend using visual partial feedback as a base. This provides continuous visual tracking, helping reduce selection time for tasks requiring high precision. Adding auditory and haptic binary feedback can improve timing and accuracy. Second, when the goal is to locate a target quickly, a mix of continuous feedback across visual, auditory, and haptic modalities can be effective. Real-time proximity feedback helps users get to the target faster. However, our findings suggest that when speed is key, adding additional feedback types like partial or binary may not be necessary and could actually overwhelm the user with too much information. Third, for entertainment-oriented applications, binary auditory feedback can be a great addition. Our UEQ skill results show it enhance the hedonic aspects of the user experience. However, keep in mind that auditory feedback alone has a minimal impact on task performance. For more challenging tasks, you might need to add other elements to boost the entertainment value. At last, in longer tasks involving moving object selection, try to minimize or avoid continuous and partial mechanisms for auditory and haptic feedback. Exposure to changing sounds and vibrations can lead to discomfort and that reducing their effectiveness over time. Thank you for your attention.